This is chapter 16 for APChem review on acid-base equilibrium and solubility equilibrium. Begin with, the chapter talks about what the common ion effect is. It says shifts equilibrium by adding a compound with an ion in common with the dissolved substance. What I'm going to do is give you an example of acetic acid dissolved in water, and then we're going to add sodium acetate to that initial acid solution to change the effect of it because of the common ion effect. Lastly, again, this will change the pH of the substance. So you see on the board, on the top, I have the dissociation of acetic acid, HC2H3O2 plus water, again double arrow because it's not completely dissolving, to make hydronium and the acetate polyatomic ion. But what happens here is if I add sodium acetate to it, remember sodium acetate is an ionic compound. There's an Na plus and a C2H3O2 minus. This is going to add more acetate ion. If you recall from Le Chatelier's principle with equilibrium, that when you add more of something, the equilibrium is going to shift in the opposite direction. So what's going to happen by adding sodium acetate to this solution that's already made, more acetate ions are going to react with the hydronium to form more of this. If initially pH is the negative log of hydronium, my initial solution without the sodium acetate would have a certain pH associated with it. When you add the sodium acetate, hydronium is going to react with the acetate ion to go back to the initial part, which means less hydronium. You are going to lower the pH by doing that. The next slide then goes over the calculation to solve for that lowering of the pH. Henderson-Hasselbalch equation is the pH equals the pKa plus the log of the conjugate base divided by the acid. So pKa is the negative log of Ka. What I'm going to do is just make up a problem for you on the board that goes over this. So I'm going to keep everything I already have on the board. Let's say for a sample case that we started off with 0.20 molar of the acetic acid. And we added to it 0.30 molar sodium acetate. And the last thing you'd have to be given in order for this equation to work out is the Ka. The Ka of acetic acid, maybe I'll write it below the acetic acid. The Ka of acetic acid given to me is 1.8 times 10 to the negative fifth. So now, if we were using Henderson-Hasselbalch equation, pH equals, now instead of writing pKa, I'm going to write the negative log of the Ka right away, 1.8 times 10 to the negative fifth. I'm going to add to that the logarithm of the conjugate base, which you recall from the last chapter, the conjugate base is the acetate ion, which 0.3 divided by 0.20, the initial concentration of the acid. When I solve for all that, I get a pH of 4.92. And if all you did prior to this was solve for the pH of just the acetic acid, it would have been a lower pH. Lower pH meaning that it would have had more hydronium in solution. Now this is very similar or builds off of something referred to as a buffer solution. Buffer solutions are solutions that have the ability to resist the change in pH. An example would be acetic acid with sodium acetate buffer. So we talked about that already. If I have that as a solution, so I drew that on the board already, how it's going to resist the HCl. If I add HCl, again, HCl will dissociate completely in water to form the hydronium ion. But now that hydronium ion can react with some of the acetate. So I'll show you on the board here what I mean by that. Again, here's my previous problem. Let's get rid of all the Ka stuff with it. If I add HCl to this, HCl in water would make hydronium and the Cl minus. But when you have the sodium acetate in there, some of that acetate can react with the hydronium to shift equilibrium back in this direction. So again, the buffer solution can both negate the effects of an acid or a base. In the acid, in this case, is able to negate the effects because the conjugate base will react with the hydronium. Now, the base is a little simpler to explain. Adding sodium hydroxide to it, well, the hydroxide that's created here, the acetic acid is going to take care of. Here's NaOH in water is going to make hydroxide and Na+. Well, hydroxide and hydronium are the acid and the base components. They can neutralize each other a little bit. So it doesn't matter if it's going to be an acid or a base, but usually, once again, we refer to a buffer solution by lessening the effect of a strong acid or a strong base. You might just have to be able to explain why it does it that way, which the base part in this example is pretty simple. The base is neutralized by the acid made from acetic acid. The acid part was a little more complicated, kind of an equilibrium idea, that with the extra C2H3O2, it's able to react with the hydronium to shift equilibrium back over. The only other thing that we need to cover in this chapter is acid-base titration curves. So NaOH and HCl is a good example of a strong acid and a strong base. Sorry that these two are flipped around. HCl is the acid, NaOH is the base. When a strong acid and a strong base are titrating one another, they reach the equivalency point at 7. 7 is what's considered neutral. As I mentioned in the last chapter, anything above 7 is a base, below 7 is an acid. Notice the titration curve that as you are titrating, again, this says milliliters of NaOH added to the hydrochloric acid. It's a very gradual slope. And once you get close to the equivalency point, you shoot up in a hurry because the number of hydronium ions are getting balanced out by the hydroxide very quickly towards the end. And once again, the equivalency point for a strong acid, strong base is 7. The moles of the acid equal the moles of the base at this point, and they balance each other out because they're both strong. This is different than if it was instead a weak acid and a strong base. Acetic acid is a weak acid, sodium hydroxide is a strong base. So again, my x-axis says milliliters of NaOH added to 50 milliliters of the acetic acid. Once again, what you will notice is the curve starts gradual. Either this curve or this curve, it doesn't matter which one we're referring to here. But then it steepens up. The difference, though, is the pH is actually above 8 in this case at the equivalency point. Once again, equivalency point referring to the point at which the moles of the acid and moles of the base balance out. The difference is, though, a strong base is going to have more hydroxide created than a weak acid. So even if the moles do balance out, you're no longer at a pH of 7, which would be considered neutral. There's more base left over than there is acid. Hence, the curve is going to have an equivalency point higher up. The last one to go over then is going to be a strong acid with a weak base. HCl, strong acid, ammonia, a weak base. Once again, if we look at the curve, it doesn't matter to me which top or bottom we're looking at here. You'll notice though the equivalency point is the important part. The equivalency point is just over 5 in this case, which should make sense because if the equivalency point is the moles of acid and the moles of base balancing out, a strong acid like HCl will be able to have more acid in the solution than ammonia's base parts. So you're going to end up with, at equal moles, it being slightly acidic still. From what I can recall or imagine, you need to be able to look at the graph and identify what is being titrated with what. I'm not putting down a weak acid, weak base example because those really depend on the Kas or Kbs if it was a base, and that makes things a little bit more complicated. But that is the short and sweet version of this past chapter, chapter 16 on acid-base equilibrium.